have discussed about this slide. We said that ISAP, subthreshold leakage current, the current from drain to source when VGS is less than VT, is much problematic for dynamic circuits. What is dynamic circuits? That is going to be discussed here. Dynamic circuit, I am drawing fresh here because earlier it is there, earlier drawn circuit, but it is clock driven circuit. This is your output node and this is N. Okay, when this circuit operates, any dynamic circuit operates with the help of clock, whereas static circuit doesn't need any clock. So this is a dynamic inverter. It works in two phases, pre-charge phase and evaluation phase. During pre-charge phase, what happens? When clock is 0, pre-charge phase is prevalent. When clock is 0, this will be off and this MOSFET will be on. Since this is let me call M E and this is MP. ME means evaluation transistor. So this evaluation transistor is off when clock is 0, and MP, the pre-charge transistor, is on. Hence the node, output node, is charged during the pre-charge phase. Okay, you know that every node is having capacitance and that can be represented by a load capacitance CL. We have discussed these things earlier also. So the CL consists of 3 components also that we have discussed. So what are those components? Can anybody tell? Harsh Tripathi, are you there? Harsh Tripathi? Harshvardhan
Yes,
Agarwal?
sir. Yes, sir.
You are Harshvardhan Agarwal?
Yes, sir.
So can you remember what are the 3 components of CL, which is not externally connected, but it is intrinsic, or you can say parasitic capacitance sometimes?
Sir, no.
Not remembering. Okay. Shashank, are you remembering?
Sir, no, sir. Like the capacitance of the transistor.
3 components.
Interconnect capacitance, drain
Yes.
capacitance, and
Who is
COS
speaking?
of fan
Who is
out.
speaking? Kartik Rai. Are you Kartik?
Himanshu, sir.
Himanshu. Okay, Himanshu Sogra. So you tell what are you are telling? You said correctly. Tell me.
Sir, interconnect capacitance, drain capacitance, and
Interconnect capacitance. Then
drain capacitance.
Drain diffusion capacitance, it is said.
Yes, sir.
Diffusion
And
cap. And third one is
COX of fan out.
COX, gate oxide capacitance of fan out gate. Very good. You have to remember things. Okay. Every time I'll not explain. So this CL or load capacitance of the output node gets charged during the pre-charge phase because MP is on, whereas pull down path is disconnected or broken because of ME off. During the evaluation phase, clock goes high. Clock becomes high. Become high, and once it is high, this will be off, and this ME evaluation time shall be on. Now, based on the input, whether it is 0 or 1, if it is 0, output should be what of an inverter? If input is 0, what should be the output in an inverter? Yes,
1, sir.
1. So you see that when input is 0, in is 0, this MOSFET is off. Hence, your pull down path is broken. Even though the evaluation transistor M is on, this is off. So pull down path is broken, and the pre-charged value or CL, which was pre-charged earlier, is going to retain that same value. Means you are going to get high here. Corresponding to in equals to 0, you are going to get output high. Out high. When in is 1 instead of 0, now it is 1. Then what is going to happen? This will be on, and already ME is on. So a pull down path is connecting the output node to the ground, and hence the CL will be discharged, and you will get output equals to 0. Is it understood? This is the working of a dynamic gate, right? I think we'll discuss later on in a more detail, but the dynamic circuit what came here to explain, I have started. So what do you understand here? During the evaluation phase, if your input here it is only one input, but in other cases maybe 3 input NAND gate, this may be the case of that the pull down network is having 3 transistors. It is shown here by this. So in this case, if any of the input is low, your pull down path is broken. So CL is not going to get path to discharge to ground. So the output node value should be ideally 0. Sorry, ideally high. Ideally high. So maybe that sometimes the input vector, when input vector is coming and evaluation is occurring, during that time anyone is low, or next time another one is low. So you don't know what input vector is going to come. So based on that, the output node may be kept high. If that is being kept high, means what? The output node is the charge stored is kept at high value only. But if your MOSFETs are having good amount of I sub, then this charge may be dropped, leaking out. MOSFETs will be leaking out through this pull down path, and hence the evaluation may be faulty during the evaluation phase. Could you understand this point? Kartik Rai? Kartik is there? Prajwal?
Yes, sir.
Okay, we'll go ahead with this. We are not going to continue here because dynamic gates will be coming later on, domino gate, etc. possibly. So during that time we'll discuss. Now we are going to discuss the MOS transistors under dynamic behavior. We were discussing static behavior. Now in static behavior, what we have discussed, threshold voltage, and then sub-threshold leakage currents, then current equations, and their derivations, etc. Mobility degradation, then velocity saturation, etc. CLM also has come in the way. Now we are going to discuss the transistor under dynamic behavior. Mainly in this we are going to discuss the capacitance of the MOSFET. We have discussed to some extent. We have also seen the I think the small signal model. Now once again we are going to revisit it. Okay, and we'll go fast. Okay, so the dynamic response of a MOSFET transistor is a sole function of the time it takes to charge, discharge the parasitic capacitance. Just now we discussed something like CL, component of CL. That has to be charged and discharged. That you remember, when the digital circuit is being operated, then that is the main function happens. CL will be charged and then discharged based on the input vector. So the parasitic capacitance that are intrinsic to the device. It is not externally connected. CL is not connected externally because it is not desirable things. Okay, and the extra capacitance introduced by the interconnect. See, interconnect he has told the extra capacitance by interconnect lines. A profound understanding of the nature and behavior of these intrinsic capacitance is essential for the designers for high quality digital integrated circuit. Okay, if you don't understand where from these parasitics or undesirable capacitance are coming, then you will not be able to handle it properly. They originate from the three sources. The basic MOS structure, that is drain diffusion capacitance of both the MOSFETs. In this case, if I talk about, then this is one. Let me take a different color. This is going to PMOS is going to offer the drain diffusion capacitance, and this NMOS is going to offer the drain diffusion capacitance. And what is drain diffusion capacitance? We have discussed earlier. Are you remembering? Himanshu?
Yes, sir.
Okay. So that thing is talking about basic MOS structure. Will offer that thing, and then channel charge. This we have not said. When MOSFET is off, see, immediately the gate voltage is 0. Okay, and when before being off, the channel was full of charge. Okay, where those charge is going, that also offers some capacitance that we have ignored earlier, not discussed. So author is telling that is also the one component. And the depletion regions, we already have seen that depletion region offers around the drain or around the source, gives the capacitance because of depletion regions of the reverse bias PN junction. Drain and source, both drain diffusion capacitance and source diffusion capacitance, we say this all. So it is useful to have gate oxide capacitance as large as possible from IV perspective. What does it mean? We say that CL smaller is better, but COX higher is better, because your ID equals to mu n COX W by L VGS minus VT whole square. Okay, by 2. If COX is higher, then current supplied by the MOSFET will be higher, and hence load capacitance can be charged and discharged very faster, and circuit is going to be faster. Okay, so the statement says that it is useful to have gate oxide capacitance as large as possible from IV perspective. Okay, the total value of the capacitance is called the gate capacitance CG and can be decomposed into two elements. One part of CG is due to the channel charge and the another part is due to the overlap. The overlap capacitance we have not discussed so far. Okay, so we'll discuss that also. Here you see, when you form the diffusion region by ion implantation. And after that ion implantation, you heat up. That is, annealing process is done. I think in the last class only you are discussing annealing is performed after ion implantation to what? For what it is done? Annealing. Can anybody say?
Sir, to increase the
maximize the diffusion.
To increase the n plus diffusion depth. This xj you can say junction depth. We call it junction depth. Okay. This depth is called junction depth. So to get the final depth of diffusion regions, see one terminology you are using, drain or source diffusion, capacitance we are saying. Okay, why we are telling diffusion term, whereas we are doing the ion implantation? Actually, before ion implantation came into use, earlier when MOSFET was invented, or at the early years of CMOS technology, the diffusion process was used. Diffusion process means you have taken the substrate and you want to make certain area n plus. So other portion you have covered with silicon dioxide and then silicon dioxide and some other material like photoresist, etc. Silicon nitride also. At the bottom, silicon dioxide, then silicon nitride at the top. Then this material is kept in place with the help of photoresist. There will be positive photoresist, negative photoresist, etc. And it has to be exposed to light. Then you have to develop in a solution, liquid solution. Then if it is positive, then those exposed portion will be washed away or rinsed away. Other portion will be hardened. Like that, some process are there to keep this portion, to cover the area in which you don't want to do the ion implantation. In other portion, what do you do? You keep the material here, P-type, sorry, phosphorus, for example. Phosphorus, to make this region N plus type or this region N plus type. So you are placing on top of the substrate, you are placing phosphorus and then heating up, and it will be diffusing gradually, and you will get this kind of shape you will get. Okay. So this was the technique initially, but later on the ion implantation process has been developed and those equipments have been used, and now it is called ion implantation. And there are several advantages of ion implantation over diffusion. Like, first of all, the lateral diffusion is less, or hence the compactness of the device. I mean, in a small space, you can make more MOSFETs. That also is possible in ion implantation. And exact dose of, phosphorus can be implanted. Precise dose can be implanted. That all are there. Various 4-5 advantages are there. We are not going to discuss all those things. So that's why, even though nowadays it is ion implanted, but still the term drain diffusion or source diffusion region, we say these are the diffusion regions, right? It is coming from the beginning. Like MOSFET, metal oxide semiconductor. Now metal is not used in the gate, but initially when MOSFET was developed, at the gate material was metal. Okay, so name is coming from there. Even though now it is polysilicon at the gate, but still that previous name is prevailing. Are you understanding, Prajwal?
What was the previous name, sir? What was the previous name of gate?
Your voice is not clear. Please clearly tell once again.
You were saying that it used to be called something else previously.
Previously, see, a diffusion process was adapted to make the N plus region. Okay, keep the phosphorus on top of this region and it will be diffusing towards the substrate. So name was diffusion. This region's name was diffusion region. Okay, drain diffusion region and source diffusion region. That same is still used, even though nowadays diffusion is not used. The process name is now
Ion implantation.
Ion implantation. That is the thing I am telling. Okay, like earlier MOSFET, metal was used at the gate. Now it is poly. Still MOSFET term is used. Historically, it is called MOSFET. Okay, so anyway, I am getting diverted. See, due to the lateral diffusion during annealing, this much length, say xd, it is denoted xd, and this side also xd. See that dimension at the top. xd. This much overlap is occurring with the gate and gate oxide. So due to this overlap regions, you have the overlap capacitance. Okay, your channel capacitance will be from here to here. This will form the channel capacitance, but overlap may be also there, especially in early processes when there was no self-aligned process. In today's self-aligned process, this overlap is minimal or negligible. Anyway, so this, of course, you can see that length of the device is getting reduced. That is one thing. First thing. Second thing, overlap capacitance also occurs. It also gives rise to a parasitic capacitance between gate and the source, gate and gate and the drain. That is called the overlap capacitance. This capacitance is strictly linear and has a fixed value. It is denoted with CGSO or CGDO. The source side, it is source side, it is drain side. And it is equal to what? COX into XD into W. COX, gate oxide capacitance, whatever is what? COX is what? Your epsilon 0, epsilon R by COX, right? This is the value. It is farad per meter square or centimeter square or micrometer square. Remember that. So that if you multiply with area is what here? This is the width of the device. Okay, W, and this is the XD. So area will be XD into W. Could you understand this point?
Yes, sir.
And it can be denoted as COW. Since XD is the technology dependent parameter, it is customary to combine it with the oxide capacitance to the overlap capacitance per unit transistor width, CO. More specifically, it is CGSO or CGDO. Capacitance of the MOSFET at its different mode of or region of operation. when MOSFET is cut off, linear and saturation. When the MOSFET is cut off, then capacitance CG, C is nothing but CGB, body, say body terminal is this side, and you have the side here in between. Okay. Let me denote here between this two plate. One is gate here, poly, other one is SI. This N MOSFET, if I say it is N plus N plus. So P type, lightly doped SI, that is another plate. So this between G and B, you have a capacitance which can be called as body capacitance. Okay, get to body capacitance, or you here it is denoted as CGC, get to channel capacitance. Okay, perhaps the most significant, most parasitic circuit element, the gate to channel capacitance CG, varies both in magnitude and in its division into three components: CGSO, CGCSO, CGCD. Means CGCH means this side, source side capacitance. Actually, what happens in resistive region, this part is associated with source and it is denoted as C, channel capacitance associated with source, and other one it is associated with drain, and this part is called CGC, channel capacitance associated with drain. That is the notation here. In other book you will find different notation, so don't go by any difficulties. If you read different, okay, and CB, the gate to source, gate to then gate to body. This is gate to body capacitance. We could say CGB only, but he's adding one term, channel. Okay, capacitance associated with body, you can think of. And these capacitances, these three capacitances are dependent on mode of operation of the MOSFET. This varying distribution is best explained with the help of diagram. Here, a diagram is given. When the transistor is in cutoff, no channel exists. There is no channel inversion layer here. Okay. And the total capacitance CG appears between the gate and the body. I mean, maximum capacitance occurs in a MOSFET in its off state, and that capacitance is CGB, we can say. Okay, body capacitance, gate to body capacitance, you can say. Okay, simply I can write CGB. We have written earlier also. Can you remember the small signal model we are discussing? During that time we have discussed or not?
Yes.
Okay. So notation during that time I was using CGB because that author has used that way. Shedra Smith and Razavi. Okay. Here C he has put telling channel capacitance. Okay. In the resistive region, when the drain voltage is VDS is 0, or I mean VDS is less than VGS minus VT, during that time an inversion layer is formed as shown here, which acts as a conductor between source and drain. I mean, it is conductor between this. When this inversion layer is absent, there is no conducting path. Okay, why? Can you tell why there is no conducting path? In this case, there is no conducting path from
That it is
source to
pinched off.
drain. Source to drain, there is no conducting path. Why are you saying that? Because it is P-type lightly doped, P-type Si. It is semiconducting material. Still, you are telling that it is not giving the conducting path. What is the reason?
Sir,
it is pinched
VDS
off.
present thermal voltage.
Could you understand my question? Could you understand my question? Your
Sir,
substrate
inversion
is
layer did not happen in cutoff.
nay. I am telling that it is not there, but I am also telling that P-type Si. It is semiconducting substrate. Then it is not insulator. My question is, it is not insulator. Then if it is not conductor like aluminum or copper, but it is semiconducting material, it is P-type. Remember that. Even intrinsic silicon is its resistivity is in between conductor and insulator. Here we have doped it with P-type or trivalent type dopant. So conductivity has even increased above the intrinsic silicon. Then why you are telling that there is not conducting path from source to drain? Could you understand my question? Harshvardhan Agarwal, are you there?
Yes, sir. Sir,
Could you-
what will happen there means, sir, there will be a very little inversion layer, sir, that is negligible.
Suppose
the
gate voltage is
negative ion
zero.
will be
So
formed.
see, let me say gate voltage is 0, and it is, we are saying that it is cut off, and we are also saying that there is no conducting path. Why? Even though we have a P-type silicon substrate. Shashank, can you say something on this?
Sir, if drain is positive and gate is 0, then it is reverse biased.
Yes, here is the answer. You have the reverse bias junction here. This junction around this is reverse biased, and hence there is no conductivity occurring from this part to this part. Here is the answer. Good. Let us go ahead. In the resistive region, an inversion layer is formed, this case, which acts as conductor between source and drain. Consequently, CGCB equals to 0, the earlier one, because this conducting path inversion layer is shielding the body, and it is being sheared this as if you have a connection here for this, for the top plate, and for the bottom plate you have given connection here. Bottom plate is attached in this way and top plate is this one. Similarly to the right side also you have a contact here for the top plate of the capacitor, and bottom plate, for the bottom plate you have another, this bottom plate means from here to here. Okay, from here to here it is divided equally, and hence the capacitance CG I could write CG CGH, but he is putting C. Okay, let us go with that, and equals to CG CD. They are equal. Okay, they are equal. Whatever value was here in this case, CGC, I mean, I could write CGB, it is getting divided equally, and the body is obscured or shielded. Hence, this value becomes 0 now. This value of capacitance becomes 0. Rather, now it is divided in two parts. One is associated with source, another one is associated with drain, and they are equal. Okay. If I write this one in this case of this as C ox into WL. WL is the area. Okay. Then it will be what? Half of C ox WL. Is it understood? Values will be given in the next slide, possibly. Finally, in the saturation mode, the channel is pinched off, and here in this region, you don't have channel, I mean inversion layer. So this capacitance CGCD for Rabe, it is like this. Otherwise, I prefer to write CGD. It is 0. But here, since this region has gone beyond this middle point, so its value is, that is CGCS, or let me write CGS as we have already denoted with this, equals to 2/3 of Cox WL. In saturation region, we don't have the capacitance associated with the drain, but we have capacitance associated with source, and that is 2/3 of this value when we say that get to body capacitance. Could you understand these points? Kartik Rai?
Yes, sir.
Harsh Tripathi is there. Still he is absent.
Sir, he said he will be back in 2-3 days.
Okay, is serious? Or any other problem? I mean,
There is some problem in his
health problem? Okay. Okay, going to the next slide. I hope you have understood. See, when the gate voltage is 0, there is no channel, and the capacitance CGCB, or I will denote that CGB is maximum, equals to WL into Cox. Okay, maximum value of capacitance. Now, if you increase the VGS gradually from 0 towards threshold voltage, it is dropping. That body, I mean, gate to body capacitance is dropping, and at VGS equals to VT, channel is formed, and you have the CGCS equals to CGCD, and obviously it is half of that value. This value is half. WL into COX, W by 2, I mean divided by 2. And total, of course, total capacitance, of course, is remaining same. This channel capacitance means this is C, this is equals to CGCS plus CGCD. Okay. Simply you can write CGS and CGD. Okay, as we have earlier used. This is what when you put VDS equals to 0 and you increase the get to source voltage VGS. VDS you have put 0 here, means MOSFET is going to be in linear region. MOSFET will be, and the channel will be just like this one, parallel. The inversion layer will be like a rectangular shape. It is rectangular shape. But when you increase the VDS from 0, you increase the VDS, and when it becomes VGS equals to VGS minus VT, VDS equals to VGS minus VT. At this point, this ratio is becoming 1. Before that, it is less than that, means still it is not fully saturated. At this point, it is saturated. Once it is saturated, and you see that the capacitance, which capacitance? You can say the CGS or CGCS is going to be 2/3 of COX into WL, and CGCD or CGD is going to be 0. Of course, total capacitance at any point, that is total channel capacitance CGC, is the summation of these two capacitance. Okay. So any doubt in this plot or a discussion? If no, then I'll go ahead. Same thing is, described. What the last sentence telling? A designer looking for a well-behaved linear capacitance should avoid the operation in this region. In this region means when VGS equals to VT. About that, capacitance changes drastically. So the author is suggesting that a designer looking for a well-behaved linear capacitance should avoid this region operation. For a constant value of capacitance, we should not operate the MOSFET at this voltage point, VGS, but say in other region. Okay, VGS should be say greater than this value. So you will get the constant value of these capacitances. That's all we have discussed. The values of the various capacitances are summarized here, and you can have a look in cutoff. PCB is Wx into Wl, that is the area, and in in other cases, other resistances, CGCS and CGCD are 0, and total capacitance, total channel capacitance is nothing but the same value. And CG, it is considering the overlap capacitance also, two sides, so 2 XD is there, so it is 2 COW. Similarly, resistive regions resistance, capacitances are given, and saturation region capacitance are given. So remember some values here and understand properly, because certain questions can be given based on this table. Now, if you want to find out the capacitance value, then it can be done by simulating this circuit. Drain and source tied together. Okay, so VDS is 0. Then if you increase the VGS, you may get the capacitance, and device will be in linear mode, and you'll get the
Sir,
tell.
so can we cover this in the next class, because it's already 9?
Okay, then we'll stop here. Next class, onward.